Today, India ranks second in the world agricultural productivity. It is a well-known fact that agriculture still employs a large proportion of India's population. However, it can be said that the technology in the field of agriculture is yet to be employed effectively to improve the productivity. Each crop is unique and has its own requirement for growth. The basic requirements for the crop's growth are suitable values of temperature, humidity, soil moisture content, and light illumination. So, it becomes a tedious process for the farmers to provide an ideal environment for the crop chosen. However, this process can be made simpler with the help of the farm automation system. Using this system, optimal values of the above mentioned physical parameters are maintained. Thus, it reduces the manual effort put in by the farmer. As a part of the literature survey, a visit was made to a village called Oragadam near Chennai. There, a farmer was interviewed about the practical difficulties of farming. He revealed about all the irregularities faced by the farmers during agriculture. All the necessary data was gathered during the brief interview with him. First, he had doubts about the feasibility of this project. After detailed explanation, he was gratified about the same and was very much interested in implementing it in his farm.
The farm automation system is basically segregated into three levels. Each level in itself is a subsystem which works independently. This is the field level, which is situated in the field. The field level consists of all the sensors. The sensors are used to measure all the basic parameters like temperature, moisture, humidity, and light. These values are sent to the next level using the Xbee transmitter. The blue module at the center is the Xbee transmitter. The white sensor at the bottom left is the humidity sensor, and this one is the moisture sensor placed inside the soil to measure the moisture level of the soil. The next level is the monitoring level, which receives the data from the field level through Xbee. The data received by the Xbee shield connected to the Arduino board is sent to LabView. This enables the monitoring of various parameters by the farmer. The third level is the control level. The various outputs are controlled using a separate Arduino board. The outputs are controlled with the help of relay circuits. The outputs are dependent on fuzzy logic, which is obtained from the LabView coding to the Arduino board. Here, the fuzzy inputs are soil moisture level, relative humidity, and temperature, whereas the fuzzy outputs are drip system and the sprayer system. Multiple field levels can be controlled using a centralized control level. This is the front panel of the LabView program. 4 parameters, namely humidity, temperature, moisture, and light intensity, are monitored continuously. The values of these parameters can be noted from the meters shown in the front panel. At this point, when the LDR is closed to show changes in the parameters, the graph also has a dip. Here we can also notice that the status of the artificial lighting system is turned on during the same period. This is because of the reason that the light intensity had gone down below the set value during this period. Similarly, the variations in other parameters will affect the output of the system based on a fuzzy algorithm. The farmer is provided with an option to change the set value according to the need of the crop. Also, the level of water, if required, as in case of a rice crop, can also be set. The values of the parameters can be noted from the meter on the right, whereas the changes of the parameters with respect to time can be noted from the graph plotted on the left. The values from the sensors at the field level are received every 10 seconds. Hence, the graphs and the meters are updated every 10 seconds. The actuators used are 2 separate 12-volt DC pumps for the drip and the sprayer system. When the soil moisture level goes below the set value, the drip system is activated as shown here. The reason for having a set value is that the actuators are not turned on for small changes in the moisture level or for the humidity or temperature. When the drip system is actually set up in the agriculture field, it will look something like this. Using drip irrigation is beneficial in many ways. Higher efficiency of water and fertilizer use. Better uniformity in water distribution, especially on plot edges. There is no wind influence, hence the system can be used at all hours of the day. No water waste on plot edges, thereby reducing weed growth between crop lines. Reduction of foliar diseases. Higher yields up to 25% mainly due to uniformity and efficient fertilization. The automation of such a system will add to the advantages and thereby increase the efficiency. This system is also used to fertilize the crop. The sprayer output of our prototype is shown here. This, when implemented on a large scale, will look like this system. Although water is used in photosynthesis, most of the water taken by the plant is used in transpiration. That is, the water is taken by the roots and evaporated through the leaves into the air. This process cools the plant. The relative humidity in the air can affect the flow of water through the plant. The higher the relative humidity, the slower the transpiration. Hence, the sprayer system is used to increase the humidity, thereby reducing transpiration. The artificial lighting system is based on the LDR input from the field. This is again triggered with the help of relay connected to the control level. Although we had used normal light for our prototype, the use of glow light, which emits electromagnetic spectrum appropriate for photosynthesis, can increase the fertility of the crop. The system has been equipped with the provision of uploading data in the server. Uploading of data is done with the help of LabView to the database. This has been done in order to maintain a log of data. This feature is really useful when it can be implemented in agricultural research. These readings of parameters are uploaded for every 10 seconds. A SQL command is then created. This command enables the uploading of data in the server, which can be easily accessed by any ordinary web browser. The various field parameters can be used as an archive that can be used for future processing in case of studies or research.